Right, this is the Betz criterion or Betz limit derivation. So this is a way to get an estimate for the maximum power that can be extracted from a wind turbine for a given flow of air. So this links to the calculation where in the lecture slides we saw that you can estimate the total amount of power that's contained within a particular flow of fluid. So this extends from that, and this looks at the realistic limit of power that can be extracted by a turbine. So what we do to determine this is we consider a position at the turbine where we have an area AT swept out by the turbine blades, and at this point we ascribe a wind velocity UT. Upstream from this, so the incoming wind velocity has a velocity u0, so this is the starting point of the velocity of the wind, and then downstream we have a wind speed velocity uf that's going to be below the turbine velocity, and that in turn is going to be below the initial velocity. And while the area swept out by the turbine blades is a defined sort of area by a physical thing, we then ascribe a mass continuity area, so that is, say, an area through which the same mass of fluid flows at the same rate, by having areas A0 for the upstream position and AF for the downstream position. So what we've got is the velocity, the final point, the downstream, is less than at the turbine, and this is less than the initial velocity, and this means that by mass continuity, AF must be greater than AT, which must be greater than A0. Okay, so as I say, these areas are defined, so we maintain continuity of mass. So this means that M0 dot equals MT dot equals MF dot equals basically m dot, where m dot is dm by dt. So this is our mass flow rate. So the previous equation we saw for the overall flow of fluid was that the power delivered was a half times the density of the fluid, the area through which it flows, and u0 cubed. And our continuity equation told us that m dot was equal to the density, the area, and the velocity. So we can substitute this into this equation here. So we end up with a term that is P equals a half m dot u0 squared. Okay, so this is essentially the rate at which kinetic energy is deposited at the turbine by the incoming wind flow. So we can say that the initial sort of condition is P0 half m dot u0 squared. The final power at the F position is Pf half uf squared. So this is essentially change in the rate of kinetic energy delivered with time. So the power that's given to the turbine must be the difference between the initial and the final conditions. So we can say that the power delivered to the turbine from a kinetic energy standpoint is u0 squared minus uf squared. Okay, so what we've considered here is purely just the kinetic energy. So we'll call this equation A. We can also think about the power and the force that's going to be delivered on the turbine by considering the momentum change, as we did for the case where there was no turbine. So our rate of momentum change, P equals density A u0 squared. So this is the same equation as before. So, and again, if we consider at P0, this must be density A0 u0 squared, which is the same as our mass times u0. And similarly, for the final position downstream, we're going to end up with m dot uf. Okay, so for the turbine, we can say that the force acting on the turbine is the total momentum change, the rate of momentum change anyway. Oh sorry, they should have dots above them there. So m dot u naught minus uf is the force on the turbine, and the power that relates to this is the force times velocity. So the power on the turbine from a momentum standpoint is F ut. So this becomes m dot u naught minus u f times by ut. So we'll call this equation B. Then now we can equate equation A and equation B because they're both giving us the power at the turbine, just coming at it from different angles. So we end up with m dot u naught minus uf times by ut equals a half m dot u naught squared minus uf squared. So we've just put A and B equal to one another. We can then do a bit of simple cancellation. So the m dot terms cancel out, and the u naught uf term will get us to lose the squared terms here. So this leaves us with ut equals a half u naught minus uf, like that. Okay, so we'll call this equation C. Right, so looking back at equation B again, we had the power delivered by the turbine was m dot u naught minus uf times by ut, and we can substitute in our mass continuity term, which was density, area at the turbine, velocity at the turbine. So this will give us Pt equals density At ut squared u naught minus uf, and we can also substitute in for C. So from equation C we can rearrange to say that uf equals 2 times ut minus u naught, where we've just rearranged this equation to get it in terms of uf, and then we can substitute into here to eliminate this uf term. So this gives us an equation where we have, let me work this out, Pt equals density At ut squared, and then this becomes u naught, it's minus uf, so it's plus u naught, and then minus 2 ut. Check that's correct, yep. So then bit of rearrangement, Pt equals 2 density At ut squared, where we've just brought the 2 out from inside the brackets to ut. That's not a very good u. There we go. Okay, so we'll call this term here equation D. Now, okay, I'm going to move down the page a little bit. Now, what we want to do is define a parameter that we're going to call A. Now, A is the fractional decrease in wind speed at the turbine. So, as a percentage or a sort of ratio decrease of how much it goes down at the turbine position. So this is given by, so we'll call it A, and it's the difference between the initial wind velocity, the wind velocity at the turbine, and then we just divide this by u naught. So this just gives us a normalized value here. So if there's no decrease in wind velocity whatsoever at the turbine, then this is 1. If there's a 100% decrease in wind velocity, this term's 0. And we can rearrange this equation to say that ut is 1 minus A times by u naught. And the reason we do this is we want to get rid of this ut term in this equation and put everything in terms of u naught, because we want a term for the power at the turbine just in terms of the initial wind velocities it's coming in. So we put this into equation D, and we do a bit of rearrangement, and we end up with Pt equals 4A 1 minus A squared, and then times by half P AT U naught cubed. Okay, so I've just plugged this into here for UT and rearranged the terms to get to this equation here. Okay, now the key point here is to recall that this term here is essentially the maximum power in a wind flow for an unobstructed column of air. So this was given by PA U naught cubed. So this term here is the one that's responsible for the decrease in power generation by the wind turbine. So we say that this term is the coefficient of power extraction. So we call it CP, and we say that CP equals 4A times 1 minus A squared. So we can rewrite the turbine power equation as CP multiplied by half density AT U naught cubed. You'll see that in some textbooks. So we want to find the maximum power that we can get out of the turbine. So that occurs because the turbine area we're assuming doesn't change. The incoming wind velocity we're going to assume is constant. So the only way we maximise the power is by maximising this CP term. So obviously CP will be at a maximum when dCP by dA equals 0. So in order to do that, we sort of multiply out these brackets a little bit. So CP equals 4A times A squared minus 2A plus 1, which equals 4A cubed minus 8A squared plus 4A. So then if we do dCP by dA, this gives us 12A squared minus 16A plus 4. And we set this to 0, and when we solve this, this means that A equals either 1 or 1 over 3. So this means that obviously if A is 1, then this solution here is trivial because it's just the same as our incoming wind power equation. So the actual solution is that A equals 1 over 3. So then we can plug this value back into the CP equation, and CP equals 4 times a third times 1 minus a third, 3's gone crazy, squared, and when we work this out, this comes out as 0.59. So then this goes into our equation here. This is the maximised version, so PT equals 0.59 times a half density AT U naught cubed. So this is the Betz criterion, or the Betz limit, and this is the maximum power that can be extracted by a wind turbine. We have the sort of Betz coefficient here, the density of the incoming fluid, so this is just air density usually, although this equation does hold for a water turbine as well. The area swept out by the turbine and the velocity of the incoming airflow. So what this gives you is for an incoming wind velocity, you can then calculate the maximum power that could theoretically be extracted by a wind turbine.